Some landscapes feel unreal, as if Earth briefly suspended its own rules. In the Karakum Desert, the Darvaza gas crater burns without interruption, an immense crater of fire glowing against the night, fueled by natural gas rising from deep beneath the surface. For decades, it has remained lit, transforming an accidental collapse into one of the planet's most surreal spectacles. In the United States, concealed within a narrow shale grotto, eternal flame falls sustains a steady flame beneath cascading water. Fire persists where it should be extinguished, sustained by invisible gases seeping through ancient rock formations. And in India, along the cliffs of Nanagat waterfall, monsoon winds can overpower gravity itself. Powerful updrafts drive entire sheets of water back into the air, creating the illusion of a waterfall flowing upward, mist spiraling skyward instead of descending into the valley below. A desert that burns like a furnace, a waterfall that shelters a flame, a cascade that appears to defy gravity. And these are only a fraction of the extraordinary phenomena scattered across our planet. How many landscapes remain hidden beyond familiar horizons? And how many natural forces are still capable of reshaping what we believe is possible? This is a journey to impossible places, where geology, energy, and atmosphere converge to create scenes that feel less like Earth and more like another world. At the historic mountain pass of Nanagat in Maharashtra, India, the waterfall emerges primarily during the monsoon season, when moisture-laden air masses from the Arabian Sea are forced upward along the western escarpment of the Western Ghats, triggering intense orographic rainfall that feeds temporary cascades over sheer basalt cliffs, rising hundreds of meters above the valley floor. As precipitation during peak monsoon periods can exceed 2,000 to 3,000 millimeters annually in this region, runoff rapidly surpasses the infiltration capacity of the rock surface, allowing water to consolidate into defined vertical streams rather than diffuse surface flow. What distinguishes this site, however, is not merely the presence of seasonal water, but the aerodynamic conditions that can alter its trajectory. When wind velocities approach or exceed approximately 20 meters per second, descending water columns fragment into fine droplets, and the resulting increase in air resistance becomes sufficient to redirect portions of the flow upward along the cliff face. This apparent reversal of the waterfall is therefore not a defiance of gravity, but a direct consequence of fluid dynamics, in which droplet size, wind velocity, and drag force interact within a confined topographic corridor that amplifies atmospheric acceleration. Geologically, the cliffs are composed largely of basalt formations associated with the Deccan Traps, dating back roughly 66 million years, whose layered and near-vertical profiles provide an extended free-fall distance that enhances the wind's capacity to interfere with the falling water mass. In effect, the combination of steep relief, channelized wind flow, and low permeability volcanic rock transforms Nanagat into a natural demonstration of the interplay between atmospheric energy and surface hydrology. At the same time, Because the waterfall is entirely dependent on seasonal rainfall, rather than a perennial river system, it can diminish rapidly or disappear altogether once precipitation falls below the threshold necessary to sustain surface runoff, underscoring the transient character of what appears, during peak season, to be a stable and powerful cascade. This variability also introduces tangible risks. Wet basalt surfaces become highly slippery, dense spray can significantly reduce visibility, and strong gusts may compromise balance along narrow, inclined paths. Beyond its hydrological spectacle, Nanagat holds historical significance as an ancient trade route marked by rock-cut caves and inscriptions, meaning that a visit to the site situates observers at the intersection of volcanic geology, monsoon climatology, and early commercial history. In this context, the image of water seemingly driven upward does not represent a suspension of natural law, but rather a moment in which atmospheric dynamics become visible enough to challenge human intuition, while remaining fully governed by measurable physical principles. Located in the heart of the Karakum Desert, the Darvaza gas crater appears less like a geological depression and more like a controlled inferno embedded within an otherwise flat expanse of sand. The crater measures approximately 69 meters in diameter and about 30 meters in depth, forming a near-circular cavity whose walls expose unstable sedimentary layers saturated with natural gas. Its origin traces back to 1971, when a Soviet drilling operation inadvertently collapsed into an underground cavern filled with methane, prompting engineers to ignite the escaping gas in order to prevent the uncontrolled spread of toxic emissions. What was expected to burn out within days has instead continued for decades, sustained by a steady subsurface supply of methane migrating upward through porous rock strata under pressure gradients within the basin. At combustion temperatures that can exceed 800 degrees Celsius near active vents, the crater functions as an open-air oxidation system in which hydrocarbon molecules react continuously with atmospheric oxygen, converting chemical energy into heat and light with remarkable stability. Moreover, the desert environment contributes to the persistence of the flames, as low annual precipitation and limited surface water infiltration reduce the likelihood of quenching the combustion zone, while arid conditions allow gas to escape and ignite without significant atmospheric dilution. However, this apparent stability does not eliminate risk, since methane concentrations between roughly 5% and 15% by volume in air form a highly flammable mixture, meaning that any abrupt change in gas flow or wind pattern could alter flame behavior unpredictably. In practical terms, the site has evolved from an industrial accident into a remote tourist destination, yet its visual impact, an illuminated crater visible against the night desert sky, remains inseparable from the geological forces that sustain it. Ultimately, Darvaza is not extraordinary because it defies natural law, but because it reveals, in a concentrated and persistent form, how subsurface energy reservoirs can manifest dramatically when human intervention intersects with the dynamics of a hydrocarbon-rich basin. Hidden within Chestnut Ridge Park in New York State, The Eternal Flame Falls presents an unusual convergence of hydrology and geology, where a small waterfall descends over shale layers, while a natural gas flame flickers persistently at its base. The cascade itself is modest in scale, dropping roughly 9 to 12 meters over Devonian-age sedimentary rock. Yet the phenomenon that draws attention is the methane seep emerging from fractures beneath the overhang. This gas originates from deeper hydrocarbon-bearing strata and migrates upward through fissures in the shale, eventually reaching the surface where it can be ignited, producing a flame that may rise several centimeters high depending on gas flow and wind conditions. Although the flame often extinguishes due to spray or fluctuating gas output, it can be relit because the seep continues releasing methane at a steady, albeit low, rate driven by subsurface pressure differentials. What makes the site particularly compelling is the juxtaposition of opposing elements: flowing water that promotes cooling and extinguishment, and combustible gas that sustains localized combustion at temperatures capable of exceeding several hundred degrees Celsius at the core of the flame. This coexistence is made possible because the methane emission point is partially shielded within a small rock recess, reducing direct water contact while still remaining close enough to create the visual paradox of fire beneath falling water. From a geochemical perspective, the seep reflects the slow migration of thermogenic gas trapped within organic-rich shale formations, demonstrating how ancient marine sediments, compressed and heated over millions of years, continue to release energy in trace but measurable quantities. At the same time, the site carries inherent risks, since methane air mixtures within the flammable range of approximately 5 to 15% by volume can ignite unexpectedly if gas accumulates in confined spaces near the rock face. In practical terms, Eternal Flame Falls is accessible via hiking trails rather than remote desert travel. Yet its scale does not diminish its scientific significance. Instead, it condenses large-scale geological processes into a small, observable setting. The persistence of the flame beneath a waterfall does not contradict physical law, but rather illustrates how fluid flow, gas migration, and combustion chemistry can intersect within a narrow geological niche to produce an image that challenges intuition while remaining fully governed by measurable natural principles. Located in Yellowstone National Park, the Grand Prismatic Spring is the largest hot spring in the United States and one of the most visually distinctive hydrothermal features on Earth. The pool spans approximately 110 meters in diameter and reaches depths of around 50 meters, with water temperatures near the center commonly exceeding 70 degrees Celsius due to continuous geothermal heating from a shallow magma reservoir beneath the park. What gives the spring its concentric bands of vivid blue, green, yellow, and orange is not mineral dye, but thermophilic microorganisms whose pigmentation varies according to temperature gradients and light exposure along the cooling margins of the pool. At the intensely hot center, where temperatures approach the upper tolerance limits of most life forms, the water appears deep blue because it is relatively clear and absorbs longer wavelengths of visible light, while toward the edges, decreasing temperatures allow microbial mats to flourish and produce carotenoid pigments that shift the color spectrum. This stratification represents a precise biological response to thermal variation measured in degrees Celsius over relatively short horizontal distances, effectively turning the spring into a living thermal map of microbial adaptation. Beneath the surface, superheated groundwater circulates through porous volcanic rock, dissolving minerals and transporting heat upward before venting through the spring in a steady, convective cycle that maintains both temperature and chemical composition. Despite its calm appearance, the hydrothermal system is inherently dynamic, as changes in subsurface pressure or seismic activity can alter flow rates and surface expressions, and the thin crust surrounding such features may be unstable and dangerously hot. In this way, Grand Prismatic Spring does not merely present a spectacle of color, but serves as a visible interface between deep geothermal energy, surface hydrology, and extremophile biology operating within tightly defined thermal limits. Located in Panjin, Liaoning Province, the Red Beach is renowned for its vast, crimson landscape that emerges not from sand, but from a seasonal transformation of coastal wetland vegetation. The striking red coloration is produced by Sueta salsa, a halophytic plant species that thrives in saline, alkaline soils and shifts from green to deep red as salt concentration increases and temperatures decline toward late summer and early autumn. This chromatic transition is driven by the accumulation of anthocyanin pigments within plant tissues, a biochemical response that helps protect cellular structures from high salinity and intense solar radiation, effectively turning environmental stress into a visible adaptation. The wetland itself forms part of the Liao River Delta, where sediment deposition, tidal influence, and freshwater inflow interact to create expansive mudflats that periodically flood and drain according to tidal cycles measured in meters. As salinity levels fluctuate across the delta, microtopographic differences determine where Sueta salsa can colonize, producing broad red expanses interspersed with lighter channels and reed beds, thereby creating a natural mosaic shaped by hydrological gradients rather than human design. Although the surface appears stable from a distance, the substrate consists of water-saturated sediments that can be unstable under load, and access is therefore restricted to designated walkways to minimize ecological disturbance and physical risk. Ecologically, the site supports migratory bird populations that depend on the wetland's nutrient-rich environment, linking the visual phenomenon to broader coastal ecosystem dynamics governed by sediment transport and tidal energy. From a geomorphological perspective, Red Beach represents a transitional zone between terrestrial and marine systems, where riverine sediment supply and coastal processes remain in continuous negotiation. Ultimately, the red expanse is not an artificial spectacle, but a seasonal manifestation of plant physiology responding to measurable environmental stressors, demonstrating how biochemical adaptation at the cellular level can scale up to transform an entire landscape into a phenomenon that appears almost surreal, while remaining firmly rooted in coastal wetland dynamics. Located on Ailmalk Island in Palau, Jellyfish Lake is a marine lake isolated from the open ocean, yet still connected through fissures in the surrounding limestone, creating a semi-enclosed basin where biological evolution has unfolded under unusually stable conditions. The lake spans roughly 0.057 square kilometers and reaches depths of about 30 meters, with stratified water layers that limit vertical mixing and establish distinct ecological zones. Over thousands of years of relative isolation, the resident golden jellyfish, Mastigius papua et pisoni, have evolved a dramatically reduced sting as the absence of major predators removes selective pressure for strong venom, allowing energy allocation to shift towards symbiosis and growth. Each day, millions of jellyfish migrate horizontally across the lake following the sun's trajectory, a behavior driven by their symbiotic relationship with photosynthetic dinoflagellates that require consistent light exposure to produce nutrients. This daily movement can cover several hundred meters, forming dense aggregations that pulse rhythmically through the water column in response to light intensity gradients measured in lux rather than tidal currents. Beneath the upper oxygenated layer, however, the lake transitions into an anoxic zone containing hydrogen sulfide at depths generally below 15 to 20 meters, creating a sharp chemical boundary that restricts safe human activity to surface waters. The vertical stratification is maintained because the lake's limited exchange with the ocean prevents full circulation, allowing density differences between layers to persist and sustain both the symbiotic surface ecosystem and the chemically distinct lower zone. Although swimming among non-lethal jellyfish appears benign, sunscreen residues, physical disturbance, or excessive tourism pressure can disrupt the delicate balance of light penetration and nutrient cycling within the basin. In this context, Jellyfish Lake is not merely a curiosity of harmless, gelatinous organisms, but a contained evolutionary system where hydrological isolation, chemical stratification, and symbiotic biology interact within precise environmental thresholds that remain measurable, fragile, and dynamically interdependent. Located near Juneau, Alaska, the Mendenhall ice caves form within the margins of the Mendenhall Glacier, a dynamic ice mass approximately 21 kilometers long that flows outward from the Juneau ice field. These caves are not permanent geological voids, but transient meltwater conduits carved by pressurized streams that channel beneath and along the glacier, gradually enlarging tunnels through mechanical erosion and thermal exchange. As surface temperatures rise above 0 degrees Celsius during warmer months, meltwater percolates through crevasses and moulins, accelerating along subglacial pathways where frictional heat and turbulent flow further sculpt the interior into vaulted chambers and sinuous corridors. The resulting ice walls often display intense blue hues, a consequence of dense glacial ice absorbing longer wavelengths of visible light while scattering shorter blue wavelengths, particularly where air bubbles have been compressed out over time. However, the structural stability of these caves is inherently unpredictable, since glacial ice is a viscous material that deforms under its own weight and responds continuously to temperature fluctuations and internal stress redistribution. Roof sections can thin to less than a meter in places, and sudden collapses may occur when meltwater flow shifts or when external warming alters the load-bearing integrity of the ice ceiling. Furthermore, the glacier itself has been retreating over recent decades, reflecting broader climatic trends that reduce annual accumulation relative to melt, thereby altering both the size and accessibility of the cave systems from year to year. While the visual impression suggests a frozen cathedral carved in solid permanence, the environment is in fact a fluid interface between solid ice and moving water, governed by heat transfer, gravitational flow, and seasonal energy balance. In this sense, the Mendenhall ice caves are not static attractions, but temporary expressions of glaciological processes, where measurable variations in temperature, discharge rate, and ice thickness determine whether a chamber exists, reshapes, or disappears entirely within a single season. Located along the coast of Fort Bragg, California, Glass Beach is a shoreline where what once began as decades of discarded glass has been transformed into a field of smooth, wave-polished fragments. Throughout the early and mid-20th century, this stretch of coast functioned as an informal dumping site, and large quantities of bottles and household glass accumulated along the rocky edge of the Pacific. Over time, constant wave action, tidal movement, and abrasion against sand and stone gradually broke the debris down into small, rounded pieces, removing sharp edges and producing the frosted surfaces seen today. Rather than remaining hazardous waste, the material was reshaped by mechanical erosion, demonstrating how persistent hydrodynamic energy can alter both form and texture through repetitive impact and friction. The result is a mosaic of translucent fragments in shades of green, brown, and clear, their coloration reflecting the original composition of consumer glass rather than natural mineral processes. Although the beach appears visually striking, most of the larger deposits have diminished due to collection and conservation measures, and removal of glass is now restricted to preserve the site. In this way, Glass Beach represents an unusual intersection between human impact and natural reworking, where coastal processes have converted industrial remnants into a landscape that feels curated by nature itself. What seems at first like an impossible shoreline is ultimately a reminder that even artificial materials, when exposed to sufficient time and kinetic energy, can be reshaped by the same forces that sculpt cliffs and carve coastlines. Located near the town of Gryfino in northwestern Poland, Crooked Forest is a small grove of pine trees distinguished by an unusual and highly uniform curvature at the base of each trunk. Rather than growing vertically from the ground, The trees bend sharply in a similar direction before curving back upward, creating a sequence of J-shaped forms that appear almost deliberately sculpted. The trees were planted in the early 20th century, and the deformation likely occurred when they were still young and structurally flexible. Although no definitive documentation survives, the prevailing hypothesis suggests intentional human intervention, possibly to produce naturally curved timber for furniture or boat building. Environmental factors such as heavy snow, gravitational stress, or phototropic response have been considered. Yet the consistency of the bend across dozens of trees indicates controlled mechanical influence rather than random natural distortion. What makes the crooked forest compelling is not its scale, but its precision. The deformation is systematic, localized, and absent in surrounding stands of forest. It stands as a subtle reminder that even slight alterations applied at an early stage of growth can permanently redirect structural development, leaving behind a landscape that blurs the line between natural growth and engineered form. Rising from the western plains of Madagascar, Tsingy de Bemaraha forms one of the most structurally extreme karst landscapes on Earth, where thousands of razor-sharp limestone pinnacles rise densely together in formations that resemble a petrified forest of stone blades extending across the plateau. From above, the terrain appears almost metallic in texture, yet at ground level, it reveals a compressed network of spires and fissures that transform simple movement into a calculated negotiation with balance and spatial awareness. The geological foundation of this landscape dates back to a time when the region lay beneath a shallow tropical sea, allowing thick accumulations of calcareous marine sediments to lithify gradually into massive limestone layers over millions of years. Subsequent tectonic uplift elevated these deposits above sea level, exposing them to atmospheric conditions and initiating an extended phase of chemical weathering driven primarily by rainfall. As slightly acidic rainwater infiltrated natural fractures within the limestone, it dissolved the rock along vertical joints, progressively widening cracks and isolating narrow ridges between deepening crevasses. Over immense timescales, this dissolution intensified vertical relief and sharpened the remaining rock ribs into blade-like pinnacles, some reaching significant heights while remaining separated by steep, shadowed chasms. Unlike smoother karst landscapes shaped by broader erosion and soil accumulation, the Tsingy's dramatic geometry persists because rapid drainage limits sediment cover, allowing rainfall to sculpt exposed limestone surfaces directly and preserve their serrated edges. What appears chaotic at first glance is in fact structurally controlled, with fracture orientation and bedding planes dictating the alignment and spacing of the formations. Ultimately, Tsingy de Bemaraha stands as a precise demonstration of how tectonic uplift, carbonate solubility, hydrological flow, and deep geological time can interact to transform ancient seabed sediments into a vertical labyrinth of stone defined by both fragility and enduring structural order. Located south of Luang Prabang, Quang Si Falls unfolds as a multi-tiered cascade that appears less like a single waterfall and more like a stepped hydrological system descending through dense tropical forest. Unlike vertical plunge falls driven purely by height, Quang Si spreads across broad limestone shelves, allowing water to spill outward in layered curtains before collecting in a sequence of vividly turquoise pools below. The distinctive coloration of these pools is not a photographic illusion, but the result of mineral-rich water flowing over carbonate rock, where suspended calcium particles scatter sunlight and enhance the blue-green spectrum visible at the surface. As water moves downstream, dissolved minerals gradually precipitate, reinforcing natural travertine barriers that shape each basin and maintain the stepped architecture of the falls. Hydrologically, the system operates through a balance of seasonal rainfall and groundwater contribution, with monsoon periods intensifying discharge and dry seasons revealing more defined terrace structures. The limestone substrate plays a decisive role by slowing erosion relative to softer rock types, ensuring that the cascades maintain their broad, tiered geometry rather than collapsing into a single erosive channel. Ecologically, the surrounding forest canopy regulates microclimate conditions, moderating evaporation rates and preserving water clarity despite fluctuating flow volumes. At the same time, the relatively gentle gradient of the terraces reduces kinetic energy compared to high vertical waterfalls, allowing sediment to settle and sustaining the clarity that defines the site's visual impact. What distinguishes Quang Si Falls is not sheer height, but structural harmony, where geology, mineral chemistry, and hydrological flow interact to create a cascade that feels architecturally composed rather than violently carved. The result is a system in which water continuously reshapes its own pathway, reinforcing the very limestone formations that guide its descent. Nestled within the arid coastal desert of southern Peru, Huacachina appears as a ring of palm trees in reflective water, isolated within an immense expanse of wind-sculpted sand. From above, the settlement looks improbable, a concentrated pocket of life surrounded on all sides by towering dunes that rise in smooth, sweeping curves shaped by persistent desert winds. At the center of the oasis lies a natural lagoon sustained by groundwater emerging from an underlying aquifer. Unlike river-fed systems, this water source depends on subsurface hydrological balance, where infiltration from distant Andean runoff slowly migrates through permeable sediments before resurfacing in the lowest topographic depression. The surrounding vegetation survives because the water table intersects the surface at precisely this point. The dunes encircling Huacachina are not static formations, but dynamic aeolian structures. Wind transports fine sand particles up the gentle windward slopes and deposits them along the steeper slip faces, gradually shifting the contours over time. Their height and curvature are controlled by prevailing wind direction, grain size distribution, and seasonal climatic variability, creating one of the most visually dramatic dune landscapes in South America. Huacachina endures because of equilibrium rather than abundance. The oasis exists where groundwater pressure, evaporation rates, and sediment dynamics briefly align within an otherwise hostile desert system. What appears to be a romantic desert refuge is in reality a delicate hydrological anomaly sustained by geological structure and climatic precision. Rising above the plains of southwestern Anatolia, Pamukkale appears at first glance like a frozen cascade of snow spilling down a mountainside. From a distance, the terraces resemble layers of ice or limestone carved by glaciers. In reality, this brilliant white landscape is the result of mineral-rich thermal waters flowing slowly over the slope for thousands of years. The process is driven by calcium carbonate carried in solution within hot spring water emerging from underground faults. As the water reaches the surface and cools, carbon dioxide degasses into the atmosphere. This shift in chemical equilibrium forces the dissolved calcium carbonate to precipitate. Over time, the mineral hardens into travertine, gradually building shallow basins and stepped pools that trap thin sheets of flowing water. Each terrace forms through repetition rather than sudden geological violence. Thin mineral films accumulate layer by layer, creating smooth, curved rims that guide the water into delicate cascades. The constant interplay between flow rate, temperature, and evaporation determines the shape and clarity of each pool. Even minor changes in water distribution can alter the structure of the terraces over decades. Pamukkale is therefore not a static formation, but a dynamic hydrological system. Its striking appearance is the visible outcome of geochemical deposition occurring in real time. What looks like a surreal winter landscape in a Mediterranean climate is in fact a precise balance between groundwater chemistry, atmospheric exchange, and gravitational flow acting with persistent consistency across centuries. Rising within the volcanic highlands of East Java, Kawah Ijen presents a landscape that appears almost engineered for spectacle. Under the cover of night, electric blue flames ripple and surge along fractured crater walls, as if liquid fire itself had shifted color. What observers witness, however, is not molten rock. It is streams of sulfuric gases escaping from subterranean chambers at temperatures exceeding several hundred degrees Celsius. These gases ignite instantly upon contact with oxygen in the open air. The result is a luminous combustion effect that is rarely visible anywhere else on the planet. At the center of the crater lies one of the world's largest hyperacidic volcanic lakes. Its opaque turquoise surface appears deceptively calm. Beneath that surface is water saturated with dissolved sulfuric and hydrochloric compounds. These compounds are formed through the continuous interaction between rising volcanic gases and accumulated rainwater. The process establishes a volatile chemical equilibrium. It transforms the crater into both a geological reservoir and an active reaction chamber governed by pressure gradients, gas flux, and thermal exchange. Along the crater floor and steep inner slopes, bright yellow sulfur deposits accumulate as escaping gases cool and condense. The material solidifies into mineral formations. Local miners manually extract these deposits. They carry heavy loads along narrow and unstable paths. They operate in an environment where toxic fumes, high temperatures, and unstable terrain converge. This reality makes Kawa Ijen not only a site of rare geochemical visibility, it also stands as a stark demonstration of how human labor intersects directly with extreme natural systems. What distinguishes Kawa Ijen is not the scale of its eruptions. It is the clarity with which it exposes processes typically hidden beneath Earth's crust. Combustion chemistry becomes visible. Atmospheric reactions turn incandescent. The internal heat engine of the planet can be observed in real time. Even the most surreal landscape here remains the product of measurable thermodynamic and chemical principles operating with relentless precision. Located along the shores of General Carrera Lake in southern Chile, marble caves form a network of sculpted caverns where mineral-rich rock meets glacial water in a display of striking natural symmetry. Over thousands of years, wave action generated by fluctuating lake levels has eroded the calcium carbonate shoreline, gradually hollowing out tunnels and chambers through persistent hydraulic abrasion. The marble itself originated as limestone deposited in an ancient marine environment, later subjected to heat and pressure that recrystallized the rock into dense, veined marble with distinct structural integrity. As glacial meltwater filled the basin, the constant oscillation of waves against the rock face began carving smooth concave walls, arches, and vaulted ceilings that reflect the lake's turquoise coloration. The intense blue tones visible within the caverns are influenced by suspended glacial silt in the water, which alters light penetration and amplifies color saturation depending on season and sunlight angle. Because erosion occurs laterally at the waterline rather than vertically, the caves maintain rounded contours that appear almost polished, reinforcing the illusion of deliberate architectural design. Unlike subterranean cave systems formed by underground dissolution, the marble caves are shaped at the interface between open water and exposed rock, making them a rare example of lacustrine erosion sculpting solid carbonate stone into accessible, wave-carved chambers. The result is a geological structure defined not by sudden force, but by sustained mechanical energy acting incrementally over extended timescales. Located within Hoh Rainforest, the Hoh Rainforest represents one of the most intact temperate rainforest ecosystems in North America, where annual precipitation levels sustain an exceptionally dense canopy dominated by Sitka spruce and western hemlock. The forest structure is defined by vertical layering, with towering conifers forming the upper canopy, while a thick understory of ferns, shrubs, and young saplings occupies the filtered light below. Moisture-laden air masses moving inland from the Pacific Ocean are forced upward by the Olympic Mountains, cooling and condensing into sustained rainfall that feeds the hydrological cycle supporting this ecosystem. This consistent atmospheric input maintains high humidity levels year-round, enabling extensive moss growth that drapes branches and trunks in thick, green veils. Decomposition proceeds slowly in the cool, damp environment, allowing fallen logs to function as nurse logs that host new plant growth and recycle nutrients directly into the soil matrix. The interplay between precipitation, temperature moderation, and biological succession creates a system where biomass accumulation and decay remain in dynamic equilibrium. Unlike tropical rainforests driven by heat, the Hoh Rainforest thrives because of climatic stability and persistent moisture supply, demonstrating how latitude, topography, and oceanic influence can converge to produce a lush biome within a temperate zone. The result is an ecosystem structured by atmospheric circulation patterns as much as by biological competition. Situated on Middle Island off the southern coast of Western Australia, Lake Hillier is one of the rare natural lakes whose water displays a persistent and striking pink coloration, visible even from aerial perspectives. Unlike seasonal algae blooms that temporarily alter water color, the hue of Lake Hillier remains stable throughout the year, indicating a consistent biological and chemical balance within the lake's hypersaline environment. The coloration is widely attributed to a combination of salt-loving microorganisms, particularly Dunaliella salina algae and halophilic bacteria, which produce carotenoid pigments as a protective response to intense sunlight and high salinity. These pigments absorb portions of the visible light spectrum, leaving the reflected light dominated by pink and reddish tones that saturate the lake's appearance. Geographically, the lake is separated from the Southern Ocean by a narrow strip of sand dunes and dense coastal vegetation, creating a semi-isolated basin where evaporation rates exceed freshwater input. This isolation allows salinity levels to remain extremely high, providing the precise ecological conditions required for the microorganisms responsible for the lake's unusual color to thrive. What makes Lake Hillier remarkable is not only its color, but its stability, demonstrating how microbial ecosystems can fundamentally transform the visual identity of a landscape when environmental variables such as salinity, sunlight intensity, and water chemistry align within a narrow ecological range. At the northern base of Mount Fuji, the Fuji Shibazakura Festival reveals one of Japan's most visually striking seasonal landscapes, where vast fields of Shibazakura spread across the ground in dense carpets of pink, magenta, and white blossoms. Unlike taller flower species that grow vertically, Shibazakura expands horizontally along the soil surface, forming low mats of vegetation that gradually merge together into broad, floral mosaics covering the terrain. The plant's growth pattern is central to the spectacle, as each cluster sends out creeping stems that root into the soil and slowly extend outward, allowing the field to thicken and expand season after season. Over time, these interconnected mats create the illusion of a continuous living surface, where color gradients can be arranged deliberately to form sweeping patterns and geometric floral waves across the landscape. Climatically, the region provides an ideal balance of cool spring temperatures, volcanic soil, and consistent sunlight, conditions that encourage dense blooming during a narrow seasonal window that typically lasts only a few weeks each year. During this period, millions of small blossoms open simultaneously, transforming what would otherwise be ordinary farmland into a vivid display visible across large distances. In addition, the positioning of the fields beneath the symmetrical volcanic silhouette of Mount Fuji creates a powerful visual contrast between delicate, ground-level vegetation and the massive geological structure rising behind it. This juxtaposition reinforces the scale of both elements, making the flowers appear even more vibrant against the muted tones of the surrounding terrain. Ultimately, the Shibazakura fields illustrate how botanical growth patterns, seasonal climate cycles, and deliberate landscape planning can combine to create a temporary environment that feels almost surreal in its color intensity. What appears from afar to be a painted surface is in fact the synchronized flowering of millions of small plants responding precisely to seasonal environmental cues. Across the rolling countryside of Luoping County, vast expanses of canola transform the landscape each spring into a continuous sea of bright yellow stretching across valleys, hills, and terraced farmland. From elevated viewpoints, the fields appear almost surreal in scale, with millions of flowering plants forming uninterrupted bands of color that flow across the terrain like a living topographic map. The visual intensity of the fields is driven by synchronized flowering cycles, where temperature shifts in daylight length trigger large sections of the crop to bloom simultaneously within a relatively short seasonal window. Because the plants grow densely and maintain a uniform height, the blossoms create a nearly solid visual layer that reflects sunlight strongly, amplifying the golden tone visible across long distances. Topography plays a crucial role in shaping the spectacle, as the fields follow the natural contours of the karst basin landscape, wrapping around limestone hills and filling shallow valleys between them. This interaction between agriculture and terrain creates sweeping visual patterns that appear almost designed from the air, yet arise naturally from the geometry of farmland, adapting to uneven ground. Beyond their visual appeal, these canola fields represent a functional agricultural system. As the flowering stage precedes the production of rapeseed oil, one of the most widely used vegetable oils in global food production. The result is a landscape where economic cultivation, seasonal climate cycles, and regional geography align to produce a scene that feels both highly productive and unexpectedly spectacular.